Okay, welcome back. Mr. Dahlstrom's Pre-AP Physics. This is the second video for worksheet number 1, train and pulley problems notes. On the front side, we did our trains, where they're either moving to the right or moving to the left. Remember, no friction on pulleys, and if that's the case, we can ignore the direction in terms of the forces that the objects are not moving in. So let's look at this one here. So here we have like a ceiling, we have just a support, could be a metal support, could be a string or rope, whatever. This is the pulley. It is frictionless, it is massless. That does affect it, and we can talk about how that could affect it in another lesson. And then we have the string that basically runs around here. So I'm going to do, the first thing I do is draw a box around each of these. And really what this is doing is this is kind of just helping us so that we don't have to draw the free body diagram off to the side here. The free body diagram is anything exists inside of this box here. So there is a tension. We talked about tensions. We really showed on the other side that the tensions are always pointing towards each other. Okay, they're pointing towards each other here because Newton's third law. And in this case here, we could see that in order for the 8 kilogram not to fall, tension needs to be going this way. Okay. Okay, tension is not pushing. If tension was pushing it down, then the string would go lax in there. So it's going up. That is T. Say, well, they're not pointing towards each other. Wouldn't this also have T? Well, ultimately, but if you think about where they're meeting at the very top there, the T basically is pointing towards each other. So this is still Newton's third law here. Remember, a pulley just redirects which way something is going, and when we meet at that contact point, or really any contact point along the way, the tensions are equal and opposite magnitude for each block. What we also have down is we have the force of gravity, or M times G. M times G. And we can, I'll say M8 times G, and we can go ahead and solve for that. So that's 8 times 9.81. So this is 78.48 newtons. And it's helpful if you do this now because you don't have to do the calculation later. Okay, that's all we have for that one. The 8 is going to go down. If it's more massive, it is the one that's going to go down. So that is going to have a negative A. So when we do MA, it's going to be 8 times negative A. Okay, and then that means that this one has to be going up, so it has a positive A. The forces on the second tension here, or the second block, is that we would have also tension this way. So that's T. And then we'd also have mg, and I'll call that m2g. That's 2 times 9.81, or 19.62 newtons. And that's it. That's our free body diagram. So because they're not moving to the right or the left, we can ignore what's happening right or left. We can just look at the up and down. So look at the M8, or 8 kilogram one. The reason I'm writing M8 is that if we wanted to, we could also solve this algebraically, meaning that if you didn't have any numbers, you could still solve for these accelerations and tensions in terms of other ones and having that there. Though you don't want us to write mass because there's multiple masses. Okay, up minus down. Even though it's going down and moving down here, it's up minus down. Up is T minus everything down. Down is the force of gravity, which we calculated is 78.48 newtons. That equals, remember, M times A, or 8 times negative A, or if you want to simplify it, it's just negative 8A. So I look at that and says that this object is moving in the negative direction. In this case, negative direction is down, so that's what that signifies. Okay, but I make sure you know why that is. It's m times a, mass times acceleration, 8 times a negative acceleration, negative 8a. And I want to solve for tension here, so I'm going to add 78.48 over. And then I'm going to pause there. You might see where this is heading. This is very similar to this, where we went and found tension, and then we set it equal to each other. Let's now write the equation for the 2 kilogram. M2 equals 2 kilograms. Up minus down. Up is T minus the force of gravity, which we calculated is 19.62. And in this case, the acceleration is positive, and if it helps to write here, hey, the acceleration is positive, or negative, the acceleration is positive there. This is m times a, or 2 times positive a, or just 2a. So this object's going down, this object's going up. I'm going to add 19.62 over to solve for tension. We get 19.62 equals, or it's not equals, 19.62 plus 2a. And we have that there. We know these tensions to be the same. Newton's third law says that these tensions should be the same, where the tension on the string is constant, so we can now set both of these equal to each other. Leave some space because we have to come back and solve that. So 78.48 minus 8a equals 19.62 plus 2a. Add 8 over here, and we get 10a. Subtract 19.62 over here. So add 8a. Subtract 19.62. And we get 58.86. Or rounding to 2 decimal places, 5.89. Okay. Now we are rounding here, so we need to understand that when we plug that into these tensions here, if these tensions are correct, because we rounded here, these are not necessarily going to be exactly the same. They should be within most likely a tenth of a Newton there. So let's just go ahead and check. So tension equals 78.48 minus 8 times 5.89. And then this one over here will be 19.62 plus 2 times 5.89. Do the one on the left, 78.48 minus quantity, 8 times 5.89. This is 31.36 newtons. And then over here, 19.62 plus quantity 2 times 5.89, and we get 31.4. Saying that is within rounding. If we had not rounded at all during this, we would have gotten the same answer. So that is within, like I said, a tenth of a Newton. So that is good to go for that one. Okay. We'll do the last one here, and actually this is the one I assigned in class to do. We'll go ahead and set the rest of this up, but I want you to do the rest of this, or at least find a piece of paper and solve for this. And then I'll find my work here and do the answers. Check real quick. Okay. So with this one, this sometimes is a misconception. People see, oh, the 8 kilogram one, that one won the battle, so it's going to move in that direction. So they think, oh, the 20 kilogram one, this one's bigger than 5, so it's going to move to the left. There are no other forces acting on this other than this tension here. So if there's any tension, meaning if there's any mass here, it's going to go to the right, assuming that there's no friction here. So if there's friction, it may move, it may not move. But it's always going to move whatever side is bigger. Even in the cases later where we have a problem where you may have let's say that's 3, say 3, and then that is 4. In that case, 4 is bigger than 3. It's going to rotate. So this is going to go down, that's going to go left, and that's going to go up. So we're just looking at that. We'll get to those next week. But we can see which way this one is going to go. This is going to move to the right, which is a positive A, and this is going to move down, which is a negative A. Draw our boxes around our boxes. It doesn't say here, I forgot to put there, so that's a tension. There's tension in that rope there. It just redirects it, okay? Just redirects tension. So here I would have tension here to the right, and then up I would have tension up. But this one would have weight. We don't have to take into weight here because weight is not in the direction of movement, but weight here. And so that's mass 5 times G. That's 5 times 9.81, which is 49.05. And because this is something that would be solved in class, I'm going to solve this fairly quickly here, or just not necessarily going. So I'm going to I have a lot of space, so it doesn't really matter where I write it here. So there's no other forces right or left. It doesn't matter here. No forces up and down matter. I'll write it down here. So M, I guess 20 is 20 kilograms. Right minus left, T minus nothing, or T equals 20 times positive A. It is a positive acceleration, so it's 20A, and that's my equation for that. For mass 5, which is 5 kilograms, this has a negative acceleration because it is going down. Up minus down, up is T, down is the force of gravity, which we calculated 49.05, equals, like I said, m times A, or m times negative A, so negative 5A. Negative 5A. Solve for T, add 49.05 over 49.05 minus 5A at that. Now we can plug them equal to each other, so we get 20A equals 49.05 minus 5A. Get like terms over, add 5A, 25A equals 49.05. And that means that A is 49.05 divided by 25. 1.96 or 1.962. Because we left off that little 2, and I guess I'm okay if we use it, but because I left out that little 2, it's going to cause these to be slightly different, so we'll go ahead and figure out what that is. This is going to be 20 times 1.96, 39.2. And then over here, this is going to be 49.05 minus 5 times 1.96. And this is 39.25. So once again, our tensions, even though we rounded, they're coming out within a tenth or a couple tenths of a unit. So that is good. That confirms that both of those are good to go. It's basically almost all the situations that we're going to have. We'll have some other worksheets that will come out next week. I had to create this from scratch, so they'll maybe take a little time, but I'll get something out by Monday. I'll put this up here, and I want you to watch all the way through. I have some people asking, hey, I watched the video, and I'm like, how much did you watch it? Well, I skipped to this part. If you skip to this part right here, this is not going to make any lick of sense. But if you watch the process, then you're going to know how to do it, and that's what's important. So I'm going to go ahead and sign off. We'll get these loaded up to YouTube and Schoology and get the worksheet on Schoology. And so I'll see you when you all return. Thanks.